Hello and welcome back. So before us, we've got a dynamics problem. The problem states the 30-kilogram crate shown in the following figure is being lifted by a cable attached to a winch and motor assembly at point D. Starting from rest, the tension in the winch cable increases with respect to time according to the formula T equals 36T squared plus 330, where T is in newtons and T is in seconds. For that formula, we have a large T and a small t. Large T will be in newtons and small t will be in seconds. The crate is resting on the ground the instant the winch is started at t equals 0. And we're going to answer the following questions based on the information in the problem statement. For that, we have three different things we're going to find. Velocity when t is at 2 seconds, distance or height when t is at 2 seconds, and the acceleration of the cable as it goes into the motor at t equals 2 seconds. So for this problem, we're going to write down a little bit of information that we have, such as the mass equals 30 kilograms, mass of the crate is 30 kilograms, velocity initial equals 0, position initial or distance initial is 0, and then those are when t equals 0, and large T or tension is 36T squared plus 330. So one of the first things that we're going to do is we're going to observe our sketch and draw a quick free body diagram. For our free body diagram, I'm going to cut the cables, I should say, as they come through the pulley or around the pulley that's holding up the crate. And I'll denote that by a little scratch right here. That's where I plan to cut them. And so for our free body diagram, we'll have our little pulley assembly right here, and it'll hold on to our crate, which is going to be down below. And then we'll have tension going up through here as such, and this like that, and these will both be denoted by T. And the only other force that we have acting on this crate is the force of mg going down. This is kind of more of a 1D problem since there really isn't much for force in the x, but if we wanted to, we could put in a coordinate system, a y and an x. And so for our next part, we're going to kind of cross off some workspace here so we can kind of have that. We're not crossing over our stuff. But we're going to say our force in the y, sum of the forces in the y, is going to be equal to mass times acceleration. And if we want to solve for that, so our forces will be such as the t going up and the mg going down, but we have two t's going up, so it'll be 2t minus mg equals ma, and we want to solve for acceleration. So it'll be 2t minus mg over m, and to make this a little bit simpler, we're going to split the fractions. So our final equation will end up with 2t over m minus g equals acceleration. We're going to circle this in a different color because we want to recall this equation later kind of simply. So we'll cross this off now too, so that way we have clean workspace. So moving on to the first part of our question, which is finding velocity at t equals 2 seconds. We have our acceleration equation, which we just solved for, and we're going to plug a bunch of stuff into it. So our acceleration is equal to 2t over m minus g, and we know what capital T is, we know the mass, and we know gravitational acceleration. So we're going to plug all those things in, and we will get 2 times 36 small t squared minus 330 all over the mass, which is 30 kilograms, minus 9.81, which is gravitational acceleration. And from there, we will solve it a little bit further down to where we'll end up getting 2.4 t squared minus, or plus 22 minus 9.81. This is still equal to acceleration. If we recall back to our kinematic equations, we know that acceleration equals dv over dt. And if we plug that down in here, so dv over dt is equal to our equation 2.4 t squared plus 12.19. We took 22 and subtracted 9.81 from it. Then we will multiply dt throughout, and we'll end up integrating dv equals the integration of 2.4 t squared plus 12.19 dt. For this, we'll need some upper and lower limits for our integration, and for that we will say that there's a lower limit of 0 and an upper limit of v for dv on the left side, and there's a lower limit of 0 and an upper limit of t on the right hand side. From there we'll solve, we'll plug 0, v, and 0 and t in, and we'll end up with an equation such that v is going to equal 0.8 t cubed, because we're also integrating. So we will have 2.4 divided by 3 t cubed, which resolves down to 0.8 t cubed, plus 12.19 t squared over 2. And this is our velocity equation. You could solve 12.19 divided by 2, and it would equal, I'm trying to think here. Oh, I made a mistake. Hold on. This t cubed does not belong in here. Oh, I went way too far. It'll just be 12.19 t. Just like that. So, now that we have this, we can plug in and solve velocity. Evaluated at t equals 2 seconds. And this is going to be 0.8 times 2 cubed plus 12.19 times 2. And this will result in the velocity evaluated at t equals 2 seconds being 30.78 meters per second. Let me put that, it's supposed to be. So this being our final answer for this, we'll set it off to the side. We'll put it up here. V equals V evaluated at. V evaluated at t equals 2 seconds equals 30.78. And we'll also want to hold on to our velocity equation, which I'm just going to pop back up here and say that velocity is equal to 0.8 t cubed plus 12.19 t. And let's go ahead and get rid of these other problems, this other writing for the moment, so we can move on to the second part of our problem. So now we understand that we've got the velocity equation, and our next part is finding this distance here. And so for our distance, we can recall the kinematic equation. V equals ds over dt, and we can plug in our velocity equation, which is 0.8 t cubed plus 12.19 t. And here we'll do the same thing where we're going to multiply dt across, and we'll end up with ds equals 0.8 t cubed plus 12.19 t dt. And we will separate and integrate from 0 to the variable, so 0 to s and 0 to t. And from here we will integrate our problem, and we'll end up with s equaling Let's see, 0.8 divided by 4, we're going to end up with 0.2 t to the fourth plus, here's where we'll have 12.19 over 2 t squared. And with that, this is our distance equation or displacement equation, and we can evaluate s evaluated at t equals 2 seconds is just going to be 0.2 times 2 to the power of 4 plus 12.19 over 2 times 2 squared. And one of these 2's will cancel out with that 2. So we'll end up with just 12.19 times 2. And S will finally equal, S evaluated at t equals 2 seconds, will finally equal 27.58 meters. No, meters, there we go. We'll denote that up in our corner for our answers. T equals 2 seconds. That's not how you write it, 2 seconds will equal 27.58. And so from here, if we just want to walk ourselves kind of back through it, we took our velocity equation and went all the way back to the beginning of dynamics and took our kinematic equations and plugged it in, separated it, and integrated it, which is how we ended up with our displacement equation, and then we just solved our displacement equation by plugging in what t was equal to. So now if we go ahead and delete this information, and delete, there we go. And now if we go ahead and our final problem, final part of this is going to be solving for the acceleration of the cable as it goes into the motor, which is kind of a very specific part of the problem. But we're going to take a look at our original sketch. And so if we have our point here, we're solving for the acceleration as this point goes into the motor. And you could go through and do the whole constant length thing, but there is kind of a little bit of a quicker way to do this, and that's pretend you're holding the crate. So we're gonna hold this crate in place, and we're going to lock the pulleys so they can't move, so there's no slipping or anything like that. And then we're gonna lift our crate up by 1 unit of, it could be meters, feet, inches, whichever. And when we lift that crate up, we're going to notice that the 2 cables that are attached to the crate, they're actively moving the crate. These 2 cables here will each have 1 unit of slack in them when they're picked up. And if you think about that, and you're like, okay, so my 2 cables here have a unit of slack apiece, there's 2 cables. Now we're going to go ahead and allow the pulleys to turn, pull slipping, and we're going to grab onto the cable over here, right here, and we're going to pull it out this way towards the motor, and we'll discover that we've ended up with a total of 2 units of slack. That was kind of a long-winded way of saying we have 2 active cables that are pulling up on the crate, and if we put 1 unit of slack in each of those cables by lifting the crate up, we'll end up with 2 units of slack. It makes sense, but it can be a little hard to wrap your head around. So if we want that, and we're like, okay, so we understand by inspection we have the 2 units of slack, and we can understand that, then what we'll end up with is the displacement, the distance traveled around the winch. We'll denote a bottom S, or a bottom W for that, is going to equal twice the amount that the cable moves. And we can go down the ladder in that and say the same thing for velocity to V. That should be V, not a W. VC. And we already know what VC is because we put VC up here. So now that we know what VC is, we can say, well, the velocity of that point, the point that we have way over here, this point here, as it goes in here, is going to be twice the velocity of the crate as the crate goes up. So the velocity of the winch, or that point on the cable, will be 2VC, which we can plug VC in, which will be 2 times 30.78. And this will end up equaling 61.56 meters per second. So now we have velocity of the winch, or that point on the cable, is 61.56 meters per second. And I did not write out any of my units, and that is bad. So we're going to write those down real fast. So we have them in meters per second. And if we look back up into this corner, what we have finally done is we have answered all of the questions. So this would be all of the answers to the problem. And that would be the problem done.